Good morning, everybody. This is John Miko coming to you on Monday, November 7th, I believe it is. I apologize, but we are going to miss class again tomorrow. I have to attend another funeral. It's kind of been a tough fall. Cancer took someone very close to my family, so I have to attend that funeral. So in an effort to keep moving forward here, I would like to, I'm recording this video of the homework, a couple other things, because I don't feel like I'm going to be able to prepare you for the test on Thursday, which is when it was originally scheduled. We're going to move it to Tuesday. I guess that would be the 15th of November. So Thursday we'll spend some time on that. I apologize, nothing I can really do. So anyways, let's use this time to review the homework. So, we're talking about discrete probability distributions. And when we talk about discrete probability distributions, there were two specific types that we wanted to talk about, and they were the binomial. And the binomial was discrete, meaning the number of outcomes was countable. But the thing about the binomial, it was a fixed number of trials. And that was indicated by n. On any given trial, there was two outcomes. The thing we're interested in studying is the success. The probability of success on any given outcome was p. And we're looking for the probability of x. And we did a couple of those by hand, but really what we focused on was using this formula in Excel, binom dist, and we give it four arguments. We give it x, we give it n, we give it p, and then we give a value true or false. And the true or false value indicates, is this cumulative or not? True means yes, false means no. So generally speaking, if x is equal to a value, we're going to use false in that flag. If x is less than or equal to a value, we're going to use true in that flag. If x is greater than a value, it's going to be 1 minus true. And if it's between, we're going to do, like between a and b. It depends if it's inclusively or not. But basically, it's going to be true of b minus true of a. And you have to figure out, does it include the endpoints or not, and go from there. But the same logic applies when we use something called the Poisson distribution. And that distribution is a little bit different because instead of being over a fixed number of trials, when we talk about this distribution, we are talking about a fixed region, like a period, a space, or probably more importantly, a fixed period of time. So we talked about this being used a lot for queuing analysis and those types of things. So I'd like to do a couple of the homework that I assigned. These were all on Poisson. So let's look at number 20, I think is a fair one to look at. So I'm going to bring that up here. It says the number of accidents that occur at a busy intersection is Poisson distributed with a mean of 3.5 per week. Find the probability of the following events. So when we're talking about the Poisson distribution, we know we eventually want to use this function, which we give x, we give it a mean, and we also give it that true or false flag. And that true or false flag, once again, true means cumulative, false means not cumulative. So the same logic that we use up here, we can use for this one. Now, number 20, I heard that the mean number of accidents is 3.5 per week. Okay, which isn't so bad. I guess it is bad, actually. Find the probability of the following events, no accidents in a week. So that's pretty easy. I'm looking for the probability that x is equal to 0 when the average is 3.5. So I'm going to go to Excel and let's do part A. And you'll see it's not so bad. So I'm going to make this bigger so you can see it. And we're going to use our function. X is 0, mean is 3.5. And because it's equal to 0, we're going to use false. And that tells me there's about a 3% chance. So let's make it a percentage, 3.02%. All right, so not so bad there. Let's look at part B. It says 5 or more accidents in 1 week. That's what part B says. Well, if we think about it, so the average is going to stay the same. Let's think about it. We can have 0 accidents, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I don't know, it goes on forever and ever. This is looking for the probability of 5 or more. Well, we have a flag that does a point, that's false, or less than or equal to. We don't have a flag that does greater than or equal to, but we know all of this combined is equal to 1 or 100%. So if we take 1 or 100% and subtract off 4 and down, we're going to be left with 5 and up. So that's what I want to do. I want to take 1 or 100% and subtract off 4 and down. So let's see what that looks like when we do it in Excel. Equal 1 minus Poisson. I'm going to subtract off 4 and down, so my x is going to be 4. My mean is still 3.5. And because it's 4 and down, that's cumulative, I'm going to use the flag true. And that tells me 27%. And I don't know if you ever use this, but I want to copy the format down. So there's a format painter. Click the button, and I get 27.46. Okay? Let's look at part C, or letter C. Okay, 1 accident today is what letter C says for number 20. 1 accident today. So not so bad. We can think about that. Well, x is equal to 1. That's easy. But our mean is over a week, and we're looking for 1 day. So we have to adjust our mean. So the way we do that is 3.5 accidents. Let's say there's 7 days in a week. How many accidents in 1 day? So I set it up like a ratio, and as you guys remember, I can cross multiply. I get 3.5 is equal to 7 mu. Divide both sides by 7. We get a half an accident per day as our average. So we're looking for 1 accident today. So that means if we go over to Excel, we're going to say equal Poisson. 1 is our x value. In 1 day, the average number of accidents is 0.5. And because we're only looking for 1 day, not 1 or less, but 1 day, we're going to use false. And that gives me roughly 30% chance of 1 accident. So a couple things we did there. We identified our x, we identified our average, and then we figured out how we need to enter that into Excel. Might as well do let's do number 22. The reason I want to do number 22 is the one we just did was over time, which is very common, but it looks like number 22 is over a region or space. So it says, in older cities across North America, infrastructure is deteriorating, including water lines that supply homes and businesses. A report to the Toronto City Council recorded an average of 30 waterline breaks per 100 kilometers. So that sounds like an average to me, so let me write that down. So our average number, this is number 22, our average is 30 breaks per 100 kilometers. That's some of the information given. Outside of Toronto, the average number of breaks is 15. So this is, I guess, the 2 averages. This is Toronto, and this is outside, so I guess we're better off outside Toronto. So depending on where we're looking at, we have to use either, sorry you guys couldn't see that, either that mean or that mean. Okay, so let's look at part A. Find the probability that in a stretch of 100 kilometers in Toronto, there are 35 or more breaks. So we are in Toronto, so we're going to use this average, and we're looking for the probability that x is greater than or equal to 35. So that means I need to take 1 minus the probability of 34 and down, okay, when the average is equal to 30, because we're talking about being inside Toronto. So let's go to the PC here. Equal 1 minus 34, because I want to be left with 35 and up. So I'm going to subtract off, take 1 or 100%, and subtract off 34 and down. And I get, hey, there's about a 20.3, 20.27% chance of that. Let's look at part B. It says, find the probability that there are 12 or fewer breaks. Let's see, you guys can't see that. Let me do this. Find the probability that there are 12 or fewer breaks in a stretch outside of Toronto. So that's pretty easy. So we're looking for the probability of 12 or less, and I'm talking outside Toronto, which has an average of 15. Well, all that is cumulative probability, so that becomes pretty simple. I'm going to say equal Poisson 12 when the average is 15, and I want 12 or down, so I'm going to use the flag true, and it tells me roughly 26.76%. Let's do one more. I'll do 23 as well. Kind of do that fast, but let's do number 23. So this is a time one as well. It says the number of bank robberies that occur in a large North American city is Poisson distributed with a mean of 1.8 per day. Find the probability of the following events. So the first one, we have a mean of 1.8 per day, and it wants to know 3 or more bank robberies. So probability x is greater than or equal to 3. So there could be 0, 1, 2, 3, 4. I don't know how many there can be. I want 3 or more. So what I'm going to do is cut off, take 1, and cut off 2 and down. Makes sense, hopefully. So 1 minus, take 2, 1.8 is the average, through. And I get roughly 27%. Now, I like this next one because it forces me to do a couple things that I haven't done yet, at least not in this little video. It says, part B, between 10 and 15 inclusive, that means it includes the end, during a 5-day period. So a couple things I have to do. Let me get a blank piece of paper. So I want between 10 and 15, that's my x, inclusive. That means I need to include the endpoints. That's why you see that less than or equal to. It tells me my average is 1.8 per day. So I'm looking over a 5-day period, so that means I better adjust my average. Let's do it, 1.8 robberies, that's how you spell it, for 1 day is equal to how many robberies in 5 days? Well, I cross multiply, I get the average is 9 robberies per a 5-day period. So this is my mean. This is just the period it's over. So I'm not going to use that 5. That's just, I adjusted it. So 9 is my average. So I went between 10 and 15 inclusively. Let's try to envision this. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And you think about it, I want to include 10 to 15. That's what I include. So I could find the point probability of 10, add that to the point probability of 11. That's a lot of work. So what I'd rather do is figure out a way to do that a little more simplistic. And one thing I could do is find the cumulative probability of 15 and down. Okay, so find that. That gives me 15 and down, but that's more than I need. So I'd want to cut off 9 and down. So the cumulative probability of 15 and down minus the cumulative probability of 9 and down. So what's that look like? Well, 15 and down, binom dist. 15, I mean, is 9. True, because that's going to give me cumulative probability. That's going to give me more than I want, so I want to subtract off 9 and down. So minus binom dist. Oh, why am I using binom dist? I shifted gear on you guys, I'm sorry. We're talking Poisson, I'm sorry about that. Minus Poisson, 9, 9, true. And that gives me about 40%. Okay, so 40%, roughly 39%, if there are that many robberies. Now, so you're going to watch this video. Your take-home assignment that is out here on Blackboard is still due Thursday. Okay, so do not, you're still going to hand this in Thursday. Our exam is going to be moved, though, to Tuesday, so a week from tomorrow. But your take-home assignment, which is out here, which uses binom, dist, and Poisson, under assignment, Excel projects. And where is it? It's down here at the bottom somewhere. Yours might look different. But third Excel assignment 2016. So there's 5 problems worth 20 points. It looks like the first 2 are binomial, and the last 3 are Poisson, okay? And for all these, I want the answers. I want the formulas. Remember that control tilde trick I showed you? And for each problem, just a little bit of narrative, maybe a sentence or 2, just because I want that. And that should be put into a Word document and brought to class on Thursday, all right? So it's due Thursday, still due Thursday, November 10th. Please bring that to class. What we'll do on Thursday then is we will review for our exam on Tuesday. So please watch this video. Please do this assignment. This will give you something to do. And I will see you Thursday. I apologize once again for missing. Believe me, I do not. I'd rather be in class teaching you than being at a funeral. I guess that's kind of a low bar, but I enjoy teaching. So that's kind of a bad statement. Anyways, should have stopped while I was ahead. Have a good day, and I will see you on Thursday. Thank you.